Now we are all familiar with the functioning of a FIFO-style queue data structure. Items that comes first into the queue is first one to leave. A person who enters the queue first is the first one to leave. For example, if we consider this queue that has been implemented using array, we see that this queue has 4 items, 1, 2, 3 and 4, with item 1 being at the front end and item 4 being at the rear end. Now since 1 was the first one to be enqueued, it is the first one to be dequeued. It is followed by 2, then 3 and finally 4. Because 4 was the last one to be enqueued, it is the last one to be dequeued. Now we have seen such type of examples in our previous sessions extensively, but still I just wanted to show you that I just wanted you to recall how the FIFO style of functioning works in cases of queues. Now, in our real lives, we often come across situations where we have queues that clearly violate this FIFO style of functioning. That is, an item that enters the queue first may not be the first one to leave, and there might be some priority that may be deciding when an item is processed. Let us take example of traffic. Now suppose that a traffic is stopped at a signal with the vehicles being arranged in a queue. Now when the signal turns green, the vehicle that is at the front will be the first one to leave. It is followed by the vehicle that was second, and so on. This is how a FIFO style queue works. Now what happens in case we have an ambulance that comes from behind? So obviously when an ambulance comes, all the vehicles will make way for the ambulance, a special priority is given, and the ambulance is allowed to bypass the queue and be the first vehicle to cross the crossing. So although ambulance was the last to come, it is the first to go. So clearly from the example we can see that variations in the functioning of a queue can exist. Not all queues are FIFO based. As in case of ambulance, there was a higher priority that was given to it, and based on the priority, a node or an ambulance is processed. Now, similar to the example of a traffic jam, in operating systems we have a queue of processes that are waiting for allocation of resources. And suppose a process comes into this queue of processes that with a very high priority, then obviously it will be allowed to bypass the queue and acquire the resource first. So priority queues are again very common in operating systems. If you study about them, you will realize that how essential this data structure is. So to summarize, a priority queue is a variation of a FIFO based queue data structure where the priority given to an item or to a node decides the order in which it is processed. Now if you think about the FIFO-based data structure, FIFO-based queue data structure, we may realize that it's nothing but a special case of this priority queue, where priority is given to time of arrival. An item or a node or a person that arrives first is given higher priority, and an item, node or a person that arrives late is given lower priority. So now that we know what are priority queues, we have seen how they are used and where they are used, let's now move on to the implementation of priority queues. Next. Let us now talk about the implementation of the remove method for the priority queues. As you can see, I have a sample queue that has been internally implemented using an array. So I have 4. Let us now talk about the implementation of the remove method for priority queues. As you can see, I have a sample priority queue that has been internally implemented as an array. This queue has 4 items in it, 25, 35, 45 and 55, with 55 being the rear item. Now, there are certain properties for the remove operation of a priority queue that are different from the dequeue operation about the normal queue data structure that we have studied. Let us now go through the various steps that are involved in the remove procedure. Now, we are going to dequeue, or we are going to remove items from a priority queue only when its size is greater than 0, because there is no point of removing items from priority queue if there exist no items in the queue. Now, if the size is greater than 0, I'm going to perform these 4 steps. Let us go through these steps one by one. The first step is to retrieve. Now, retrieve means to retrieve the item that is at the first position or at the 0th index of the array that has been used to internally represent the priority queue and store it in some local variable. So here at 0th index, I have item whose value is 25. I'll take 25 and I'll store it in some local variable, say x. Once I'm through with that, I can then shift all the items that are to the right of 25 one position to the left. So 35 comes at index 0, 45 comes to index 1, and 55 comes to index 3. Once I have shifted these elements, I'll then perform the update operations. And by update, I mean updating certain variables that are properties of these priority queues. The most important being the size variable. So because I have retrieved an item and I have overridden its value in this array, I'll decrease size by 1 because that is equivalent to removing the item. So now the size has been reduced. Furthermore, because of shifting, this index 3 is no longer my rear. Instead, index 2 becomes my rear. So I also decrease rear by 1. Now we have already seen what are the consequences of removing items from the 0th index or the first position of an array. We need to perform shifting, and this is a time consuming operation, but still this is a property of a priority queue and we need to do that. Now if you recall the dequeue operation for a normal queue data structure, what we did was, instead of shifting items, we were removing items from the front position, that is the position at which the front pointer was pointing. And by doing so, we have encountered a problem of empty spaces at the beginning of an array. And the solution to the problem was circular array. In this case, we do not do that. We follow the traditional approach. We'll remove from the starting position, from the 0th index, and we'll perform the shift operation. So once I have retrieved, I have shifted and updated. Now there is a possibility, I move on to check. So there is a possibility that the item that I am removing is the only item in this priority queue, and in that case, after retrieval and shifting, there exists the size of the queue will reduce to 0. So in the check operation, I will see if the size is 0 or not. And if in case the size is 0, I will set the rear variable to -1, which indicates that this queue is empty, this priority queue is empty, and nothing can be dequeued from it. Finally, in the fourth step, I will return the value that was retrieved in the first step and stored in this local variable x. So that was the remove method for priority queues. I hope you understood that. And next, I'm going to discuss about the insert method for priority queues. Now that we have seen how the remove method for the priority queue works, let us now go through the implementation of the insert procedure for a priority queue. As you can see, I have a sample priority queue whose size is 4. The size of the array that is being used to internally implement this priority queue is 5. Because the size of the priority queue is 4, there are 4 items, 25, 35, 45, and 55, with the rear variable at index 3, containing the value 55. Now, in the insert method, our first step would be to check whether the array is full or not. Only when the array is not full, we will be able to insert items. If in case the array is full, we won't be able to insert new items into the priority queue. As you can see in this case, the size of the priority queue is less than the size of the array, indicates that the array is not yet full and we can insert new items. So once we know that we are able to insert items, I will then increment the rear variable by 1 so that I can obtain a position or an index value at which new item can be inserted. So upon incrementing rear by 1, rear will point to the position in the array with index 4. So this is the new position of a rear. Once I have obtained this new position, I can then add the new item. Suppose the client of this code has invoked the insert method with an item 3. So I can then add 3 at the rear positions. Once I have done that, I will be performing some updations, the most important being the size of the priority queue, which is denoted by this variable pq size. So it is no longer 4, instead it is now 5. Once I have updated the size, I will then perform a sorting operation. Now, what does sorting mean? Sorting basically means to arrange elements in some particular order. Now, the sorting procedure that I'll be using will sort the items of the queue in ascending order. Now, why are we performing sorting? So, as we have already discussed in a priority queue, the items will not be processed in the order in which they are entering the queue. Rather, they are processed based on some priority. So for our example, I assume that items that have less value are having more priority, and items that have greater value are having less priority. So when we sort this queue, the situation will be something like this. 3 will come over here, and rear will shift to index 4 only. It will remain there only, right? So this is what the sorting procedure does. All it does is to sort the items in the ascending order, so that higher priority is given to the items with less value and lower priority is given to items with more value. Now, because 3 has the least value, it will be the first to be processed, or the first one to be dequeued, thereby proving our point that it is not the arrival time of an element that decides when it will be processed. Rather, it is the priority that decides when an element is processed. So after the sorting procedure, we can then return a value 1, which indicates that the insert operation was successful. If in case the full helper method returns false, that indicates that our array is already full, then I can return, instead of 1, I can return 0, indicating that we cannot perform the insert operation because of unavailability of space. So that brings us to the end of priority queues. I would now recommend you to go to your PCs and implement this program to see this actually works. I won't be giving you with any source code for this program because I want you guys to implement this on your own. I have shown you how the two main procedures, insert and remove, work, and because you have already seen the implementation of NQ and DQ procedures in normal queue data structure, implementing priority queue won't be much difficult for you. In the next session, I'll start with a new data structure known as trees. Till then, I'll say goodbye to you. Class dismissed.